Okay, probably no one even looked at the homework yet. So the first few are momentum questions. So the first one is inelastic collision. So, um, so for an inelastic collision, sorry, you got to look at what's going on initially and then what's going on finally. So we can sketch what's going on sort of initially because we're given some information about what's going on before they collide. So let me just tell you what's going on before they collide, what you know and what you don't know. So there's a mass moving in the positive x direction. You know the mass, and you know how fast it's going in the positive x direction. I'll sketch the velocities in a second. And you have another mass that's moving in the negative x direction, so they're going to collide. But this time, for the first problem, it's inelastically. For a future problem, it's perfectly elastic. But for this one, it's inelastic. So this one's going like this. Oops, sorry. It's supposed to be an arrow. This one's going like this. So you can say that this is like v1i. This is the initial velocity of mass 1. And this one's going to the left. And that's the initial velocity of mass 2. So this is mass 1. That's mass 2. Okay, so let me tell you what you know.
We don't know the velocity of mass 2.
Okay, so you know this one, you know mass 1, you know v1i. You know mass 2, but you don't know v2i, right? That's the thing that you don't know. However, you do know that it's going in the negative x direction. So what you can do is write down sort of a general equation for momentum, the initial momentum before they collide, right? So you should know how to do this on your own. But all you're doing is just adding the two momentums up as a vector, right? So the sign matters, which direction they're going. So the momentum of this guy is just m1 v1i. It's pretty easy. You just multiply the mass times how fast it's going. And the momentum of this one is m2 times v2i. Now it's a little bit weird how you can write how to write v2i because you know that it's going in the negative x direction, correct? So you could put in the sign now. In other words, you know it's in the negative x, and you can just write it as a negative velocity because you know it's in the negative x. But if you do that, when you eventually find v2i, which is one of the things we have to find is what v2i is, you're finding the amount of v2i because you already took into account that it was negative. If you write it here as negative. So it's a little caveat that might be a little bit confusing when you write it down. I'm going to write it down as negative because, all right, so maybe make it clear. This is plus m2, but v2i is negative because it's in the negative x direction, right? Because we know exactly that it's in the negative x. It's given to us what direction it's going. Okay, so the point is you know everything in this equation but what v2i is, right? Everything. So you can write down, you can put in the numbers that you know here right away.
They give you the momentum.
What was that?
They give you the momentum.
Well, you know both masses and v1i. The only thing you don't know is v2i. Okay, so does everyone have this? Like how you find the initial momentum? It's just the momentum of this one plus this one added together, right? It's not that hard to figure out. And so after they collide, they're stuck together, right? Because it's a inelastic collision. So you can write their final momentum. So they're basically stuck together. It's kind of like one mass moving at some velocity, correct? After they stick together. Remember inelastic collisions? So the momentum of that thing would be the total mass of both of them because it's stuck together, right? So if, one of them was like 5 kilograms, the other one was like 10 kilograms, it'd be like a 15 kilogram thing moving at some velocity, right? So the momentum of this 15 kilogram thing would be its mass times how fast it's going and in what direction it's going, which is Vf. So that's the final momentum of both of them. It's always this sort of equation for inelastic collisions, right? The sum of the masses times Vf. And then you always can use conservation momentum for any case where things collide, right? For both inelastic and elastic. Yeah. Yeah.
Oh, yeah, how I found Vf.
We're getting there. Let me just go through the whole explanation if you still have a problem. then you can ask, right? But I haven't finished telling you how to do it yet. Okay, so this is PI, and this is PF, right? This is conservation momentum. This is another key thing to know for test 4, right? How to find momentum and then how to use conservation momentum. Right, so you find the initial momentum, you set it equal to the final momentum after they collide. And you get this equation here. Now, you don't know what the question is yet. I'll tell you in a second. But I'll tell you one thing. You have to figure out V2I and VF to figure out the answer to the question, right? So if you look at this equation, from the initial momentum on the left-hand side, we don't know V2I, correct? I told you that. You also don't know VF. VF isn't given, right? Just the masses are given. So you don't know two things in this equation, right? You don't know V2I, VF. So you have to somehow find V2I to find VF, or find VF to find V2I, right? You can't just find both of them with one equation, correct? So there's something else that's given in the problem besides M1, M2, and V1I. The other thing that's given is the average force acting on mass 1, what I call mass 1, right? So does anyone remember how you find average force? This is another thing that goes together with momentum, right? How to calculate average force. Does anyone remember how to do that, or how we did it? We did it in the notes, right, a couple times. Does anyone remember how we did it?
Oh, it's something. It's a fraction, right?
Yeah.
It's like average.
So it's this. It's the impulse, which is the change of momentum. You can either write it as the impulse or the change of momentum. So if you want to find the average force on mass 1, it's the change of momentum in mass 1 divided by the time it takes to change its momentum. So the change of momentum in mass 1, the final momentum of mass 1 is M1 V1F, because after the collision, it's moving at VF, right? M2 and M1 are both moving at VF, right? Because they're stuck together. Minus the momentum of mass 1 before the collision, which is M1 V1I, right? That's the momentum of mass 1 before they collide. Yep.
I have a question. The M1 VF is the mass of both of them together.
No, they're stuck together, both moving at VF.
Right, so I'm saying like the M1 VF should be M1 plus M2.
No, you're just talking about mass 1.
Why? Because of...
That's the average force on mass 1 is all you're talking about.
Okay, fine.
Okay, so divided by delta T. Okay, so you're given, what are you given? You're given the average force, it's given. You're given the time for the collision, it's given. So what's the only thing you don't know in this equation? VF, right? Now you got to be careful with your signs because everything's a vector, right? FAB is a vector, it can be positive or negative. V1I is a vector, but it's positive, right? Because it's going in the positive x direction. So you got to be careful with your signs because these are all vectors, but you can solve for VF, right? Okay. So you carefully solve for VF, carefully, and then you plug it into here, right? Once you're done finding VF, and then you can plug it into here, and then what can you do after you find VF? And then
Find V and you get V2I.
right, then you can find V2I, right? So now you know VF and V2I, which are two things you didn't know before. Does everyone follow me so far?
Our average force was given to us, right?
What was that?
The average force was given.
Mm-hmm.
Perfect.
So the average was given in newtons, right? Okay.
Same question.
Yeah.
That's not-
Yeah, right. Okay.
Was this one more question? So once we have the average force and the time, all we need to solve for is a VF then we can get it right there, right?
Right.
Yeah.
All right. Now the question is how much kinetic energy is lost, because in an inelastic collision you always lose kinetic energy, total kinetic energy, right? So what you need to do is you need to find how much kinetic energy you had before the collision from the two masses. Everyone overcomplicates this. It's not that hard. So the total kinetic energy of both masses initially, right? So mass 1 is moving at some velocity, right, before they collide. So how much kinetic energy does mass 1 have just by itself before they collide? That's great. So this is just the kinetic energy of mass 1 before they collide, right? Mass 2 is moving before the collision. How much kinetic energy does mass 2 have before they collide? Right. You just figure out how much kinetic energy mass 1 has before they collide, figuring out how much mass kinetic energy mass 2 has before they collide, and just adding those things together, right? That gives you the total kinetic energy they had before the collision. Correct? And then you do the same thing after, right? So you got to find the K after, which is the final kinetic energy. But essentially, it's one mass, because it's two masses stuck together, right? They form one mass. So what's the kinetic energy of that one mass that's the two masses stuck together?
So it's going to be the mass of them together.
Right?
And times VF, because VF is the way they're going finally.
Right. So that's the total final kinetic energy, correct?
And then you final mass initial.
Yeah, then you you subtract them, and that's how much is lost, correct? So the key thing here is conservation of momentum, which you have to know how to use. Average force, which you have to know how to the calculator to use. And also that kinetic energy is lost in an inelastic collision, right? Those are the three main things that happen for an inelastic collision. All right, so does that make sense? All right. Yeah.
So in the kinetic energy equation, we have to put the value of VF into the equation above it to find V2I.
Right.
And should it be like a negative value? Like
It depends.
Whatever VF, yeah, whatever it is.
Because we're squaring it, nothing should be negative.
And then once we plug
One
in
difference.
Like once we plug in V2I here, then we should be able to do this.
The difference could be, I'm saying like just they both should be positive originally.
So yeah.
Okay. That's it, right? Okay. Anyone have any other questions of this one?
This is just the kinetic energy lost.
Mhm.
Yeah, to do this, do I have to subtract these two, like the kinetic energy after and before? Or
Right.
Subtract?
Mhm.
You subtract them.
Mm-hmm.
Okay.
Okay.
Okay, can I
Good.
see that after? Good.
Okay. Ready? This will be posted, right? You can just download the PDF.
Okay.
Right? Okay. So, the second one is another inelastic collision. And it's kind of a fun sort of thing. Actually, I was thinking about this the other day, and it turned into a homework problem because I wanted to figure out what's going on. So, you have a meteor, sort of an asteroid, collide with the Earth. So when the meteorite hits the Earth, it's an inelastic collision because it just buries itself into the Earth, right? So basically, what you're doing is some sort of inelastic collision between the Earth and some big meteor, which actually you don't want to have happen. So what I did is I gave you the, this is about, everything about this is pretty close to what's actually going on. So if you have a meteor with a radius, so meteors are approximately spheres, although not exactly spheres, they're approximately spheres. And a kilometer wide radius for a meteor has a massive, it's the same for everyone. It's like 9 times 10 to the 12th kilograms. 9 trillion kilograms is a kilometer. Meteor with a radius of a kilometer, right? So you have instead of having a meteor with a radius of a kilometer, you have a meteor with a bigger radius, right? And the first thing you have to do is you have to figure out how much mass this bigger meteor has. And the mass scales or is proportional to the cube of the radius because it depends, it's a function of volume. And for the volume of the sphere is the radius cubed. Well, it's 4 or 5 times the radius cubed. But anyhow, the point is, it's proportional to the radius cubed, right? So the first thing you have to do is figure out how much the mass of this bigger meteor is, right? So how would you do that, right? So it's proportional to the radius cubed, right? So if it was 2 kilometers instead of 1 kilometer, what would you do to find the mass of the 2 kilometer one? You know the mass of the 1 kilometer one. So you know the mass of the one column. It's given. It's 9 times 10 to the 12th kilograms. So how would you find the mass of a 2 kilogram?
Oh, they're proportional to each other, right? You said that.
Proportional to the cube of the radius.
So,
2 cubed.
Right, you do like 2 cubed times the original mass, right? That'll give you the new mass, right? So that's the first thing you got to do is you got to figure out the mass of the meteor using proportions.
oh, you're saying if the second one had 2 coulomb, got it.
Right.
So you take the second you take the second meteor's radius, and you cube it. And you multiply it by.
Right. So that gives you the mass of the meteor, which is going to be a big number, because masses of gigantic meteors they're a lot, right? Trillions upon trillions of kilograms. So it collides inelastically with the Earth, which we consider to be stationary, and I give you the mass of the Earth. So what we're doing is an inelastic collision. I'm skipping all the details that did the last problem, but it's basically the same idea as the last problem. You have the initial momentum of both the meteor and the Earth. So this is the meteor. Just m by itself is the meteor, right? So the meteor is moving at some velocity, which is given, by the way, the initial velocity of the meteor. That's another thing that you know how fast it's going. And you also just found the mass. Plus, it's colliding with the Earth. So it's the mass of the Earth times the initial velocity of the Earth. But the initial velocity of the Earth is 0, because I told you it's 0. It's at rest, right? This is 0, right? The Earth isn't initially moving. So what's the initial momentum? It's all due to the meteor, correct? So you can find the initial velocity, the initial momentum of the meteor, because you know the mass and you know how fast it's going. They're both given. And then after the collision, they're stuck together again, right? Just like the last one. It's the same thing that we just did. So it's basically the mass of the meteor plus the mass of the Earth times some VF, which is the speed of both of them, or the velocity of both of them after they collide. So then what do? You do conservation of momentum, and you get m1 v1I, the momentum of the meteor, is equal to that, right? That's what we did the last problem. So what you can do is you can find the final velocity of both of them after they collide. It's just the momentum of the meteor before the collision divided by the mass of the meteor plus the mass of the Earth. Now I give you the mass of the Earth in the problem. It's 5.97 times 10 to the 24th kilograms. That's what the mass of the Earth is. Now the mass of the meteor is going to be pretty big, but nowhere even close to 10 to the 27 kilograms, as it shouldn't be. What do you think you get for an answer here? So the mass of the Earth is a lot bigger than the mass of the meteor, even though the mass of the meteor is pretty big. The Earth is a lot bigger.
So velocity should be around the same.
Well, if you
It has to
do,
be
so what's the bottom?
Oh,
What
it
do-
should be proportional.
Wait.
So you c-
What's the bottom? You're adding a small number to a large number, right?
It's just the same thing. You can negate the m, basically.
Right, so the m basically goes away because this is so much bigger than that, right? So you get the mass of the Earth. Then you're dividing a small number by a big number, right? You have this m up here. So if you divide a small number by a gigantic number, what do you get? Something
Very, very small. So it's supposed to be-
very small. It's basically 0. It's not quite 0, but it's practically 0. It's like when you do it, it's going to be like 0.000 something, right?
Do the m's cancel?
They can't
No, the
cancel.
m's don't cancel.
It's just so small.
The bottom end can't cancel.
Oh, because they're adding.
Right. So as a result, when the asteroid hits the Earth, it doesn't really move the Earth. It moves it slightly, but basically 0, right? So what's stated in the problem is what happens to all this kinetic energy. So let me just say something. So at the beginning, you have the kinetic energy of just the meteor, because the mass of the Earth isn't moving, right? So the initial KE is basically all due to the meteor. So how much kinetic energy does the meteor have?
Half mv squared.
Right. Because the Earth isn't moving, right? Before. And then what's the final kinetic energy, just like we did last time? So I'm not writing final KE. It might be a little bit confusing, but it's the same thing, right, that we did last. It's M plus ME times VF squared. But what is VF, basically?
0.
0. All right. So this is about 0. Pretty close to 0, right? So the question is, where does all this kinetic energy go? I mean, you originally have a lot of kinetic energy, and then you have no kinetic energy. Well, it goes into basically destroying the planet, right? This is why you don't want a meteor hitting your planet or Earth, because it's a bad thing, especially one this big. So it's just an interesting thing to figure out. So the Tsar bomb, which is the biggest hydrogen bomb ever tested by the Soviet Union, like in the 50s, released 2.1 times 10 to the 17 joules of energy, right? That's one Tsar bomb, which is thousands of times, something like 3,000 times larger than the bomb dropped in World War II. So the question is, how many millions of Tsar bombs is this equal to? It's not just a few. It's millions of Tsar bombs. It's basically like dropping a million of the largest nuclear weapon ever made at the same point, the same time, in the same part of the Earth, right? It would basically destroy nearly everything, right? That's the point of this. So all you do is you just figure out, you take the kinetic energy lost, which is basically this, right? Just the initial kinetic energy, because there's no energy left. And you divide it by the energy of a Tsar bomb, and you figure out how many millions of, but it's in millions, right? So you get an answer like 5 million. But you don't put 5 million, you put like 5, right? Okay. So anyhow, this is why you don't want a meteor hitting your planet, especially one this big, right? Yeah.
So, can I ask a question? So you said kinetic energy initial divided by the energy of the Tsar bomb, right?
Right.
And that's the millions, right? Okay. Can I ask you also, to find, well, what is the M of the for the KE I like 1/2 M, like what is the M? Is that the M of the Earth? Is that the M of the meteor?
Mm-hmm.
The mass of the meteor is it given?
No.
Yeah. How do we find it?
Proportions.
Proportions, right?
Yeah, oh yeah, we said that to do it, we need to do like, you said if you times it by 2, like, are you gonna give us like a factor that we times it by, and
Yeah.
then we cube it?
Right. Mm-hmm.
And but what about like the V1I? Like
It's given.
That's given.
Mm-hmm.
Okay, that's given. Yeah, I'm still not sure about the M though. Like how'd you find that again? The M.
Proportions.
Yeah, but like, okay, so, but why do you cube it though? Oh, so let's say it changes from like 1 km to like 10. Like, well, why do you cube it?
Because that's how it works. It's proportional to the
Because
cube.
it tells you in proportion to the cube.
Okay.
Read the question.
So then you cube it and then you multiply it by the mass of the original
Right.
meteor.
Mm-hmm.
Okay, thank you.
Yep. Okay. So the first, any more questions on that?
So once we find our initial, we know that our final kinetic energy is 0, and our initial is the number that we get. So the change is no way to finalize our initial, and we take that and we see it compared to the Tsar bomb, and that's how we know the millionth thing.
Right.
Okay.
Okay. So the first two are inelastic collisions. So this one's, second one's a pretty straightforward inelastic collision because most of the things are 0. The third one is an elastic collision, right? So we did perfectly elastic and inelastic collision. So the third one's an example of a elastic collision. Okay, so for elastic collisions, there's 2 things you have to pay attention to. One is you have to use conservation momentum. So you use conservation momentum for both inelastic and elastic. Except for elastic, the masses bounce off one another and they're not stuck together. So basically, before they collide, let me bring this up again. What did I give you? Okay, so it kind of looks like this picture. Actually, I'm going to copy this whole thing. The initial picture for number 3 sort of looks like the initial picture for number 1. Let me make sure this. All right, so once again, you have a mass moving in the positive x direction, and you have another mass moving in the negative x direction before they collide. So it looks like this. Now the difference between 1 and 3 is that you do not know mass 1. That is not given. V1I is given. You know mass 2, but you don't know V2I, right? So there's actually 2 things you don't know. You don't know M1 or what V2I is, right? For the first part. So after they collide, so this is the same momentum, right? Because it's the same picture for both inelastic and elastic collisions, before they collide. However, after they collide, they bounce off one another, right? They're not stuck together anymore. So the momentum looks different compared to number 1. So just writing it down in general. So after they collide, mass 1 is moving at some velocity. So its momentum is m1 v1f. V1f could be positive or negative, depending on if it's going to the left or to the right. And then mass 2 has its own separate momentum because it's not stuck to mass. They're not stuck together, so they each have their own individual momentums. And that's the momentum of mass 2, right? So if you add them together, that's the total momentum of both of them before they collide. Now, all right, let me just do conservation momentum, right? So then for both inelastic and elastic collisions, you always can do conservation of momentum, which is that the total initial momentum they have before they collide is equal to the total momentum they have after they collide for both cases. It's that the total momentum after they collide is different for both cases. Because for inelastic, they're stuck together. But for perfectly elastic, they're not stuck together. So the right-hand side looks different. Yeah?
Mr. Gross, I have a question.
Yeah?
Shouldn't our V1F be negative since it's going in a negative direction?
Well, I'm saying V1F could be positive or negative. I'm going to get into that in a second here.
Oh, I'm sorry.
That's fine. Okay, so let's look at this equation and what we know and what we don't know. We don't know mass 1. We don't know V2I, exactly what it is. But we are given V1F, which is the velocity of mass 1 after they collide, and V2F, which is the velocity of mass 2 after the collision. And you know the directions too. So yes, V1F could be a negative number or whatever, but you write it in as just a negative number, right? I mean, the directions matter, right? If it's going in the negative direction, you have to write it as a negative number, right? Okay. All right, but the point is, you know V1F, V2F, M2 and V1I. Anyhow, the only thing you don't know is M1 and V2I, right? So you don't know M1 and V2I. So we have to find M1 and V2I to finish the problem. Now, what else do we know for inelastic collisions? For perfectly elastic collisions. So there's one more thing you should know for perfectly elastic collisions, just in general.
The kinetic energy stays the same.
Right, the kinetic energy is conserved, and to conserve kinetic energy, you have to have this. You have to use this equation. So it's this V1I plus V1F. This equation will be on your equation sheet. Is equal to V2I plus V2F. This makes sure that kinetic energy is conserved. You don't lose any before and after for a perfectly elastic collision. So using this equation, what can we find? Keep in mind we know the final velocities, right? We also know V1I.
We can find V1. No, we can find V2I.
Right. So you can use this equation to find V2I. That's the only thing you don't know in that equation, right? So now you know what V2I is, just using that equation. It's not that hard to figure out. You just subtract V2F from both sides, right? So that gives you V2I. Then if you know V2I, you can plug it in here, and the only thing you don't know is mass 1, right? So now you know mass 1. You can just solve that equation for mass 1. You have to be very careful with all your signs, though, right? You have to be careful here, right? Because it's easy to screw up signs. But if you're careful with your signs, you can find mass 1, correct? Now the question is, what is the average, the magnitude, right, just how much the average force is, I don't care about the direction, on mass 1. So once again, how do you find the average force? Just like we did in question 1, it's the same thing.
What's delta P1?
Yeah,
over delta?
it's the same thing. So we can just copy that. Right, so remember in question 1, we used this equation here to figure out the, well, we used it to find something. But here we're going to actually use it to calculate the average force. So now you know mass 1. And sorry, this is V1F. I just have to change this because they're not stuck together anymore. Right? Okay, so this is the momentum of mass 1 after the collision, right? Minus the momentum of mass 1 before the collision, divided by.
I have a question. We use the conservation of energy, right? The PI equals PF to find
Momentum.
M1, right?
Momentum, yeah. Mm-hmm.
So the conservation of momentum. But in my case, like it would seem they get M1 can equal any number because the mass of the two and the velocities are like opposite of each other. At least for me, because I know that my V1I, my V1F are the same, except one's positive, one's negative.
Yeah, you got to be careful with your signs, though, right?
Right. No, I'll try. We'll see what happens.
Yeah. Anyhow, you plug in the mass V1F, which is given, V1I, which is given. Right? You just need the mass to figure out the average force. It could be a negative number, but you're just finding the amount of it, right? So you don't care about if it turns out to be negative. You ignore the sign because it's just the amount of the force, right? All right. Does that make sense? Yeah.
Like what if we get confused? Like I know like the first number is supposed to be the like the V1I, and like for the V2, yeah, for like V2F and V2I, they're like listed. You list them after you tell us the seconds. Like are they listed like in order? Like so we don't get confused. Like we shouldn't like get confused by like the way you list them.
I don't think so.
Okay.
Yeah. Okay. So that's once again, right? So you have to know conservation momentum. You have to know how to use this equation for perfectly elastic collision, and then average force again, right? Okay. Okay. So does that make sense? Okay. So the first three are momentum, and then we're going to move on from momentum. And number 4 is moment of inertia question and rotational kinetic energy for point masses. So let's go on to number 4. All right, so one of the next things we did in class was rotational, well, we did constant acceleration, which actually after this one, I should have put constant angular acceleration before this one, but it doesn't really matter. But anyhow, one of the things we did after momentum is moment of inertia and rotational kinetic energy. So you have 4 masses this time, not 3. I gave you 3 in the example, but it's really not that much harder. So you have a mass that's on the negative x-axis. You don't know what this mass is. I'm going to call it M1, but you don't know M1. You know where it is, but you don't know what the mass is. And then you have another mass on the positive x-axis, M2. You know its mass and exactly where it is. You know you have another mass on the negative y-axis, M3. Once again, you know how much it is and where it is. And fourth mass is on the positive y-axis. And you also know where it is and how much it is. So the only thing you don't know is mass 1, right? What it is. You know the locations of all of them and all the masses but mass 1. So the first thing you're going to do is figure out mass 1. And how you're going to do that is you're given the moment of inertia about the origin, right? It's given to you. So how do you figure out the moment of inertia? If you're asked, if you know all the masses, right? and where they were. How do you figure out the moment of inertia about the origin? Does anyone remember doing that for these point masses? We did it in the notes. I can go back and find it, but does anyone know?
Moment of inertia?
Uh-huh.
I remember seeing this.
Yeah, it's, let me see if I can find it quick. If I can't find it quick, I'll just show you. Here it is, moment of inertia, right? Remember we did this, moment of inertia about the z-axis, so what did we do? You find the distance to the origin and then stuck it in this equation, right?
Mhm.
So it's the same thing, except there's 4 masses, right, instead of 3. So let's go back here. Sorry. So it's the same thing, right? But you have to add m1 r4 squared. Okay, so the r's are the distance to the origin, which is basically just given to you, right? You know all the r's. So the only thing you don't know is mass 1, because you're given the moment of inertia too, right? I should have mentioned that. That's given. So the only thing you don't know is m1. So you just solve this equation for mass 1, and then you know what this unknown mass is. So now you know all the masses, and you know where they all are. So the question is, if nothing changes, but they're spinning about the y-axis at some rate, what's the rotational kinetic energy about the y-axis? Okay, so what it means is that they're spinning like this about the y-axis.
Like a helicopter kind of thing, like propellers?
Right,
Cool.
like that. All right, so the rotational kinetic energy is given by this equation, right? It's 1/2. It's like the analog of typical kinetic energy. It's 1/2 mv squared, but this I is like an m and omega is like a v, so it's 1/2 I omega squared. That's the general equation. But if you want to find the rotational kinetic energy about the y-axis, it's the moment of inertia about the y-axis times how fast it's spinning about the y-axis. Now, omega y is given. That's how fast it's spinning about the y-axis. But you have to find Iy, which is the moment of inertia about the y-axis. We also did that in the notes. Remember? We did, okay, here. What's the moment of inertia about the y-axis, right? So what do you do for the moment of inertia about the y-axis?
You only take into consideration the x-axis, 'cause that's the only thing that's actually rotating.
Yeah.
The
Yeah, so the ones on the y-axis don't contribute because they're on the y-axis, right? The distance to the y-axis is 0. So that's the reason why you have to find m1, because m1 contributes to the moment of inertia about the y-axis, right? Because it's on the x-axis, right? So you use the 2 masses here to find the moment of inertia about the y-axis, right? It's almost the same equation, except that R3 and R4 are both 0, right? Because it's on the y-axis. And that'll give you the moment of inertia about the y-axis, and then you just plug it into this equation. And that gives you the rotational kinetic energy about the y-axis. Uh-huh.
A question, like to find M1 first, like that's the step, and then we use that for equation 2. To find the M first, M1, how do we find it if we don't know I?
You do know I.
Oh, yeah, well, what is, like, is it given?
You
Yeah.
calculate it.
Is the moment of inertia? Is I the moment of inertia?
Mm-hmm.
Okay, I is the moment of inertia. Okay. So, and once you find M1 from that, then you just use that equation, but shortened. Like, why do we use like M1 times R1 squared plus like M2 R2 squared instead of like the R3 and R4?
Because R3 and R4 on the y-axis, the distance to the y-axis is 0.
Okay, so we use that then for to find what? Like we just plug it in to find the new I.
Right.
And then okay. And then you plug the new I there, and then you times that by the already given.
Right.
Oh, okay.
Anyhow, the main thing is knowing how to figure out moment of inertia about any axis for point masses and also rotational kinetic energy, right? The equation for it. Okay, So on to 5. 5 is actually kind of straightforward. I'll give you a trick to do it. It's not really a trick, but anyhow. So number 5 I should actually put before 4, but it doesn't really matter. Number 5 is a constant angular acceleration problem, right? So we did the blue ray, whatever spinning. It's kind of like that one. But it's pretty straightforward, except you have to do some conversions, which is the only hard part about it. So I say an object is spinning, I should have said it about some point. It doesn't really matter. It's spinning at spinning at some RPM counterclockwise. And then it changes to a different RPM counterclockwise in some time under a constant angular acceleration. So the question is, how many revolutions does it make during this time? So let me get the equations for rotational motion, which is here, right? These equations here. Actually, I have them all. Never mind. I thought I didn't show you one of them. So you have to use one of these equations to do this problem. All right. So these are the constant angular acceleration equations, which you have to use to do this one. Okay, so you're given how fast it's originally spinning. So what is that?
Yeah.
Yeah. So it's omega I, right? You're also given how fast it's spinning at the end, which is y. You're also given a time. Okay, so it's t. And I'm asking for how many revolutions, right? So what am I trying to find out of these variables? What do you think the revolution was? Delta theta, right? Something related to delta theta. So we know omega I, we know omega f, we know t. What's the only equation which makes sense? Yeah. So I got to use this one. It's pretty simple to use. However, you have to make sure that you do conversions. So what I mean by that is you have to convert rotations, revolutions per minute, which is RPM, to radians per second first, right?
So you multiply by 60.
Almost. We did it
No, you divide by 60, sorry.
almost. You're close on both accounts. Where was it? Here.
Yeah.
You have to convert RPM to radians per second first, using what we did in this part here. It's the same thing, right? So keep it on for 1 second, right? So you can sort of copy it down, but if not, you can go to, what is this, lecture 18, the second example in lecture 18. Part A of the second example, right, in lecture 18, right? All right, that's the first thing you have to do, convert to radians per second, both the initial omega and the final omega, right? Mm-hmm. Okay.
So wait, sorry, I have a question. It says 2 pi radian. We don't know our radians, do we?
You know the RPM. You're converting to radians per second.
But it says there are 2 pi radians, right? 2 pi rad.
Mm-hmm.
What's the rad?
Radians.
Just a unit.
Just 2 pi.
60.
Yeah.
Got it, okay.
Okay, so that's not that hard to do, right? Okay, so then what you do is once you convert to radians per second, you plug it into this last equation, which is easy, right? You know the time. This is really easy to figure out once you convert them, right? But the problem is your answer will be in radians because it's radians per second times the time in seconds, you get radians. And the question is, how many revolutions does it make? Not radians. So then you got to do what we also did in lecture 18.
Convert back.
Convert to revolutions, not quite RPM, revolutions. So this is what we did, part C of number 1 in lecture 18, right? How many revolutions does the blue ray make? It's just the radians divided by 2 pi, right? 2 pi radians. Each time it goes around is 2 pi radians. And that gives you the answer in revolutions.
But you don't have to convert it back to minute. No, just asking for revolution. You just have to convert it.
Right. So it's a conversion problem, basically. To convert it to radians per minute, radians per second, and then back to revolutions, and also how to use one of the equations equation for angular, constant angular acceleration. We'll actually use it again, those equations, for another problem, right? So you'll see it again. All right, so does that make sense?
Can you post the equation sheet before the quiz?
Yeah, maybe, yeah.
Oh.
Yeah, I
Thank
could
you.
probably do it this time, yeah. All right, are there any questions on 5? It's actually pretty straightforward, right? Okay, actually 4 was pretty straightforward too, not that hard. Okay, so,
Not so bad.
Once you get
Yes.
it, they're all straightforward.
yeah, this one isn't too bad. All right.
Wait until number 8.
Yeah, no, actually they're all super bad. Okay, so 6 is total kinetic energy problem. You have something rolling down an incline, right? So you have to take into account the total kinetic energy, the fact that it's spinning and moving, right? Gives you the total K. All right, so it's kind of like what we did. Let me just borrow the sketch from, all right, this one, the total K. It's
I know which one you're referring to.
yes, it's very similar to this one.
Oh no.
Yes. So, all right. Hold on, I'm going to copy some things here.
We did that one wrong. What did we do? I don't even know. Oh.
Okay, the difference here, I'm going to change some things, but the difference here is that at the top of the incline, it's moving, right? So from what we did in class, it wasn't moving at the top. It started from rest. So there's one difference here, is that, God, okay, so sorry, one more time. So this is not 0. It's some thing that's given. Also, in the problem, what's given is the length of the incline. So this is 30 degrees for everyone. I made it easy because 30 degrees works out kind of easy. So the angle's the same for everyone. The length of the incline is not the same for everyone, but it is given, right? Okay. Now, what we're going to do is we're going to do conservation of energy, basically, right? If something is rolling down the incline like we did in class, so the 0 point is at the bottom. Now, in class, this is what we did, right? Because the total kinetic energy was 0 in class because it wasn't moving at the top of the incline. But here, it's moving at the top of the incline. So is the total kinetic energy 0 at the top of the incline? No. So what is it? It's going to be this slightly different form of kinetic energy that you have to use when things are rolling. It's 1/2 VCMI squared times 1 plus C, right? That's the difference between what you did in test 3 and what you're doing in test 4. The C value is given, by the way, right? It's given in the problem. However, we need to find the height, right? In other words, we don't know the height explicitly, but you can find it. So how do you find the height if you know the length of the incline and the
Sine.
angle? Right, right. So that's the one thing you have
So
to
this
do.
would be just half of x.
Yeah, sine 30 is 1/2, so it's just L over 2, right? It's just half the length, right? So I made it easy to find the height. Okay, so that gives you the initial energy. The final energy is going to be the same thing as what we did in class because you're at the bottom and it has no potential energy. So it just has total kinetic energy. So then what you do is you use conservation of energy. But as I mentioned in class, only static friction is acting on it, not kinetic. And the normal force does no work. So for these cases where things are rolling without slipping down inclines, EI and EF are the same thing, right? It's conservation of energy with W and C being 0. So what do you know? You know H. You know the mass, although it cancels out, so you don't really need to know the mass. But you do know the mass. You know VCMI, you know C. The only thing you don't know is VCMF, right? If you set those two things equal to one another. So that's what you find. You find VCMF, right? Which is how fast it's moving when it gets to the bottom of the incline. Now, yeah?
VCMI is given, right?
Mm-hmm. Now, the question is, what is the rotational kinetic energy at the bottom? not the total kinetic energy, the rotational kinetic energy. This is the total. So how do you find the rotational kinetic energy? Just in general, I showed you already.
1/2 I.
Right. Right. So this would be the final sort of rotational. When it gets down to the bottom, what's the rotational energy at the bottom? So there's two things you have to do. One, you have to, well, one thing isn't really yet something you have to figure out. You just have to kind of know how it works for these things rolling down inclines with I, which we'll get to in a second. But the thing you have to figure out is what is omega f, right? So does anyone know how to figure out what omega f is? We also did this. I mean, all this stuff we did in just different parts in the notes. So the question here in part C was, how fast is it spinning at the bottom, right? So how do we do that? It's right there.
So with the VCM.
Yeah, you use this, right? If it's rolling normally, then how fast it's moving is equal to its radius times how fast it's spinning, right? That's another key thing to know for the test. So then what you do is you use this equation here, right? Because you know VCMF, you just figured it out. The R is given for the problem, the radius of the disk or whatever it is given. So then you can find omega f, and you stick it in here to find the rotational kinetic energy. How does I work for things that are circular? How do we write down I? Does anyone remember? So we did it.
Isn't it like 2/5? It depends on what that's from lab.
Yeah, well,
Depends on what the tool does.
it's mentioned in the PowerPoint, so let me just show you. Okay, so I, for anything circular, it's the C value times mr squared, right? That's how you find the moment of inertia about the center. All these things are given, right? The C is given, the mass is given, the radius is given. So you just find I, you plug it in here, you find omega f, you plug it in there, and that gives you the rotational kinetic energy at the bottom. Yeah, it's not so bad. The key thing here, right, is to know how to do calculation when things are rolling, right? Total Ke, and also this thing, right? That how fast it's spinning is related to how fast it's moving, right? By that equation. All right.
Yeah, so I don't get this. Like, I right here. So let me just focus on the Ke rotational equation. To find I, it's just straightforward, like C times M times radius. And to find WF, yeah, I'm not sure how we find that. Like, do we divide?
So the initial equation on the top where we have the EF, that's how you find your velocity CMF, right? That's step one. That's the thing underlined up there. That's how you find that. Once you find that, you bring it down to your bottom formula, which says VCMF equals R times omega F. You with me so far?
Yeah.
Good. That's how you find your omega. Now, the question is how do you find I for your kinetic energy? That's when you use the equation on the right, which is I equals C mr squared. Your radius is given, your mass is given, your C is given.
So once we find the VCMF divided by R, that's where we get the UF.
Right, omega F, good.
And then we just find the I value of it.
Exactly. Yeah. Dr. Rossi got it next.
Oh.
Okay, good. Okay, we're good? Thanks. Okay, so the next couple are torque questions. So one is when the torque doesn't add to 0, and the other one is when it adds to 0, right?
Yeah.
That's the last two questions. Actually, it's usually just 6 questions, so I'm going to make a thing here to make it 7 questions. All right, so I didn't give you a sketch, but it's pretty easy to figure out from my wording, but I'll just give you the sketch here anyhow. So you have this disk. It's kind of like what we did in class. You have a disk. We did an example with torque on a disk. And it's spinning around its center. You know the mass and the radius. And you're given a bunch of forces acting on it. So one of them acts up directly above the center on the edge of the disk in the negative x direction. But you don't know what that is, right? So this is the center of the disk here, right? I'm going to try to... Is that the center? Oh, it's pretty close, right? So this force that you don't know is directly above the center in the negative x direction. So you don't know what this force is, though. That's the whole point of the problem, to calculate that force. You know another force, but you know it's given directly to the left of the center, halfway between the center and the edge in the positive y direction. So it looks like this. It's directly to the left, but halfway between the center and the edge. So it's like here in the positive y direction. I'm going to call this, well, I'll call this F1. We don't know F1. This is F2. So we don't know F1. And this is F2. So you know everything about F2. You know where it is, or where it's applied, and how much it is, right? All right, the third one is directly below the center at the edge in the positive x direction. So the third one is directly below the center at the edge in the positive x direction. So it looks like this. This is F3. And then the last one is applied directly to the right of the center in the positive x direction at the edge. So it looks like this. Directly to the right in the positive x direction. Okay, so this is the sketch. But you can kind of figure it out just from the words. So we're just looking at these forces. You're ignoring weight in the normal force because that's in the direction perpendicular to the way you're looking at it. It doesn't matter. Okay, so this is a torque question, right? So you may not understand why we're doing this, but trust me, you have to sum the torques, right? That's part of the problem. So what we need to do is just sum these torques and see what we get. Okay, so let's just do them one by one. Does anyone know how to find the torque for, say, F1? You have to do all of them, right? So
You have to find,
You have
like,
to extend the line and then.
you have to do draw the line of action, right? This picture is going to get kind of messy. I'm going to do them all together. So you just have to like follow step by step. All right, so here's the line of action, correct? All right, what's the next thing you need to do? Draw the moment arm, which goes from the axis, which is the center, to that line of action. So I'm going to color code it though. So green will be for F1. So it can't be like this, right? Because that's not perpendicular. About there is perpendicular, right? It has to be perpendicular. So this is L1. But what is that? We did this.
The radius.
The radius, okay. So we know the moment arm for the first force. We can also figure out the direction of the torque, right? Because that's the thing we also have to figure out. So what way does F1 cause this disk? If it was the only force there, which way does F1 cause the disk to rotate about the center?
It'll be counterclockwise.
Right, here we go, like this, which is counterclockwise. So it's a positive torque. So I'll write that down in a minute, but let me just sketch out all the torques, right? Okay, so that's F1, correct? Now I'm going to do the same thing for F2. So the first thing I'm going to do is going to draw the line of action. It's going to get a little bit messy, but it's not so bad if you just do it step by step. I always miss the force. Okay, it's there. So this is your line of action. Okay, so then what's the next thing you have to do after the line of action?
Perpendicular line to the
Right.
origin.
So I'll do it in orange for F2. So it's this, right?
So this is going to be half the radius.
Yes. That's R/2, right? What direction is the torque created by F2? Right, and make it rotate like this. Oops, which is clockwise, right? So it's negative. Clockwise is negative. All right, once again, we're going to do the same thing for F3, correct? So let's do F3.
So that will also be radius. Same thing.
Yep. But I'm just doing it step by step, right? So everyone sees.
Sorry.
No, that's fine.
Not all of us are as smart as you.
Stop. We're trying to get this review done. I'm not trying to insult others. I appreciate that.
All right, I'm going to move this.
We just had to.
Shh. We're on video. Stop.
It's fine, everyone hears.
I don't know where to move this. I guess I'll try to squeeze it above the thing because I have to draw the moment arm, right? So L2. All right. So then you get to draw the moment arm for this one. Do it in purple. Okay, so it's this, which has already been said, is the radius again, right? And which way is the torque for this one? Uh-huh. So that's positive.
Is F4 0, right?
Yeah, we're getting there, but yeah, it's good. So, I mean, this thing should be directly to the right of the center. I might not have drawn it perfectly, but let's see. Totally missed. I don't know how I always miss it. That's pretty close, actually. Yeah, so, yeah. So the moment arm for F4 is 0, right? Because the moment arm goes through, sorry, the line of action goes through the axis, right? So F4 has no torque, right? Only F1, F2, and F3 have a torque. So now what we can do is find the net torque, which is the sum of all the torques about the center. So this one is positive F1, right? So the torque is positive F1 times R. That's just from F1. F2 is clockwise, so it's negative. F2 times the moment arm, which is R over 2. F3 is positive because it's clockwise. So that's F3 times R, F3 times the moment arm, right? And F4 is no torque, so we don't worry about it, right? Okay, so the question is, what is F1? Okay, well, so far all we know is this equation. And in this equation, we know all the forces and the radius, right? But we don't know F1. So you have to know some other information to find the net torque. So what is the net torque equal to? Does anyone know? Just like in general?
15,000 meters.
You know, like Newton's second law for torque? Almost, well, that's if it's not rotating, right? So this one's going to be rotating. So in general, does anyone know?
Wait, let me ask you, like, the force is positive because, you know, force is applied to the, like, negative direction that makes it go counterclockwise, so that's why it's positive torque.
Mm-hmm.
Oh, okay.
Mm-hmm. So does anyone know the general equation for net torque? It's like Newton's second law.
Mass times.
Oh, it's mass times acceleration, but what is mass for? Rotation.
I times
Right. So this is how we're going to figure out what F1 is. Now, the moment inertia is kind of like what we did on the last problem. It's just a disk or something. So we can figure out the moment inertia, like C m r squared. C is given, the mass is given, the radius is given, so you know I. The thing you have to find is alpha, right, which is the angular acceleration about the center. To do that, what we have to do is use constant angular acceleration and rotational kinetic energy, because the so the disk is originally at rest, and then after these forces are applied, it's spinning and it has rotational kinetic energy. So you can figure out how fast it's spinning after the time to figure out alpha, right? So what is rotational kinetic energy? We just did it, right? We're doing it again. What's the equation? Right. So you're given the rotational kinetic energy after some time. So that'll allow you to find the omega after some time, correct? Now you know the omega, you know that it starts from rest, and you know the time it takes to go from the omega, the initial to the final omega. So we want to find alpha. So it's using these equations again. So from kinetic energy, you know omega F. You know omega I is 0 because it starts from rest. You know the time, and you're trying to find the alpha, right? So then you use this equation here. to find alpha,
So alpha's like, this is literally like velocity except for using.
right, exactly. And then once you have alpha, so you find omega, that's this omega. This is 0. And then once you find alpha, you throw it in this equation here, and that allows you to find F1, because it's the only thing you don't know after you find alpha, right? All right, so that's the steps for that one.
It makes sense, just long.
It's not too long.
It's pretty long. Like
No,
if
it's
this
not
was
too
a
bad.
quiz question, this would be already 75
Right.
minutes to go on.
Yeah, well, it's not going to be a quiz question, but parts of it might be on a quiz, right? Okay. So does that make sense? Anyhow, you have to know how to calculate individual torque, net torque. Use this equation for torque. Okay. So the last question is a question for torque, but for something in equilibrium, like the board on 2 supports. It's basically one of those questions, but there's a slight difference between the one that we did in class and the one that we're doing in the homework. So if you remember, this is what we did in class, right? That's not it. That was the review, sorry. This is it. So it's similar to this. I'm going to borrow this picture, except there's one extra thing going on. Yeah, and I'm going to get rid of all those numbers because they're different for everyone anyhow. So you're given this board on 2 supports. The length of the board is given, although it's different for everyone, but it's given. So you know the length of the board, and you know the mass of the board. You know where these 2 supports are placed. Once again, it's different for everyone, but you know where they are. So let's call this one X1. No, I don't want to use blue. I'm going to use that for the forces. Sorry. Let's call this one X1 and this one X2. So you know these things. X1 is how far support 1 is from the left end. X2 is how far support 2 is from the right end, which are given. But the difference here is that you have another force that's applied to the board in the positive y direction, some distance from the right end. So it's like here. And it's different for everyone, but actually I'm going to do it in blue. Usually the force is blue. So the difference here is that you have a force acting on this thing. Now, I should have explicitly said it was an equilibrium. But it is an equilibrium, right? It's not rotating. So this is X3, I guess, from the right end, right? There's 3 different distances. The question is, what is the amount of the support produced by the one on the left, this one over here? So we're trying to figure out what that normal force is, right? So the first thing we need to do is draw all the forces acting on the board. So obviously one of them is the normal force that we're trying to find. The other one is the other normal force we don't really care about, but it is there. And what about the mass of the board? How do you draw the weight?
Straight down the middle.
Yeah. Okay. All right, so the question is, what is the force, Fn1? That's what we're asking for, Fn1. So what do we know? What don't we know? We don't know Fn1 or Fn2. In the example, we found both of them in the notes, right? But for this specific one, I don't really care what Fn2 is at all. And it's got nothing to do with the answer. Well, I mean, in a sense, it has something to do with the answer. But I don't care about it. I mean, for the answer, you don't factor it into the answer. So remember, you can pick the axis to be wherever you want it to be for these equilibrium problems, remember? So I can pick it to be there, but that doesn't make any sense there. So I don't know Fn1. If I picked it there, would it be a smart place to put it if I put it there? No, because then I would find it gets rid of Fn1, which is the thing I want to find. It'll allow me to find Fn2, but I don't really care about Fn2. So the other smart place to pick it is here, maybe, right? If you pick it there, you get rid of Fn2. The only thing you don't know is Fn1, and that's the thing you're trying to find. So that's where we're going to put the axis to be above support 2. All right, so now what we're going to do is figure out the torques produced by Fn1, W and F, correct? So how do we do that again? It's pretty similar to what we did in class, except you got to worry about that other force, which is different, but everything else is the same. So this is, I don't know what just happened, but this is, the line of action for Fn1. Yeah, it's going to get messy. Okay, so what is the moment arm for Fn1? Remember, it's the line, I'll color code the moment arm. It's the line that goes from the axis, which is over support 2 now, to the line of action. So it's like this, right?
Mm-hmm.
So this is, let's just call it L1, or L, yeah, let's call it L1. So how would you find that, the actual
So
distance?
like of your board, you know where each support is, and you just calculate through there.
Yeah, I mean, there's different ways to do it. One way to do it is you just take the length of the board, subtract x1 and x2, right? That gives you the remaining length, right? Okay. So you can calculate L1 because it's basically given indirectly. What about the torque, the sine of the torque from Fn1? So if Fn1 is the only thing there, which way would it make it rotate about the axis that we chose? Yeah, it would make it rotate like this, right? Which is, no, clockwise, right?
So be negative.
Yeah.
My question is this though, do we not care about the force on the right?
No, we'll get there.
Oh, you did.
No, well, let me just do all the rest of it, and you can see. All right, so then we got to figure out the torque created by the weight, too. So how do we do that? All right, so you do the line of action for the weight. How am I so far off? All right, so, okay. So how do you find the moment arm for the weight? It's supposed to be right on top of the first one. I'm going to displace a little bit so it's a little bit easier to see. But how do you find the moment arm for the weight? It's like this. Did I just change it to purple? Yep. Purple. Okay. So this would be in purple. L2, right? For this, sorry, LW for the weight, right? How would you figure that? The length of that, LW.
So you know where the center is, you just take your...
It's half the length minus x2, right?
Yes.
Okay. Now, which way does the weight, what's the sine of the torque from the weight? You make it rotate like this, which would be counterclockwise, positive. So we don't worry about Fn2 because we put the axis there. That's the reason why I chose it. But we do have to figure out the torque created by the other force, right? So how do we do that? It's the same way we did it before for the other torques, right? You have to draw your line of action, which is like this. No, that was better. And then your moment arm, which I'll do in some other color. I don't know what color. Brown. Okay, so this would be from the axis to the line of action would be this, right? Oops. That would be the moment arm for that torque to be this, which is LF, right? How would you figure out LF?
X2 minus X3.
Yeah, it's just the difference of x3 and x2, correct? Now, which way would this torque, would this force cause the board to rotate?
Counterclockwise.
Counterclockwise.
Yep. Okay. So, then what you do is you find the net torque, which I'm going to try to do. So, this one was negative, the first one, right? So it's minus F1 times L1. The other two are positive, though. So this is the weight, not the mass, the weight, right? mg, weight, times the moment arm for the weight, plus F times LF. This is equal to what if it's not rotating?
0.
0, right? Because it's not rotating, so it's equal to 0, correct? So the only thing you don't know in this equation is Fn1, which is the thing you're trying to find, right?
So it's simple.
Yeah, it's pretty simple. Yeah.
Except we would never have known how it got there.
Well, you just find the torques and you just sum them, right? That's basically it. So, yeah, in the end, it's pretty straightforward, right?
Thank you, done.
Yeah, that's it. That's all 8 of them.
Thank you so much.
Yeah, I
Mhm.
still have a few questions about this.
Mortify.
It's
Yeah.
about the normal force of one,
Huh?
like on the left, to find that.
Let me just start the video.